be?
Yeah, sure. Okay.
Yep. Hi. Hi, everyone. Welcome to day 6.5 of the Poly course. I'm David Jasmyers, the other David. And I'm here again to do another special guest lecture, continuing off from last time, where I talked about the double category of arenas. So I'm going to start today by reviewing quite quickly what we did last time, and then we'll see how behaviors of systems can be composed and using the double categories of arenas as a framework. And so in particular, we're going to end with this result of David Spivak's that shows that the steady states of composite systems compose according to matrix multiplication. And we'll see that at the end, and we'll explain how that works. And if we have time, if there's a time, I'll explain how that follows from the double categorical point of view. So last time, and by last time I mean last time I was here, so that's last time, I told you about how I'm going to have two kinds of morphisms between polynomial functors. And so normally, in the rest of the class, you would have only heard of polynomial maps, or morphisms between polynomial functors. And they would be written like this. And this would be a map of polynomial functors. But because I'm going to use two different kinds of map between polynomial functors, I need two names for these things and two different ways to mark them. So I'm going to call these, the original polynomial functor maps, lenses, or dependent lenses, if I'm feeling very fancy. And to remember what one of these is, I'll write a W sharp here, is we have W, which goes from P1 to Q1. And then we have W sharp, which goes from, it takes something in P1, and then it takes something sitting over the image of that thing in Q, and it gives you back something sitting over that thing in P. So that's the first kind of morphism. That's the one you're familiar with from the rest of the course. But last time I introduced another kind of morphism, which I called a chart. And so a chart going from one polynomial to another, I'll just say it's going from P to Q. I'm going to write it with two forward arrows. And what it is it's a function on positions, just like last time. But then it's a function on directions that goes forward. So it goes from something in P1 to something sitting over it, and then to something sitting over its image. So the notation here is meant to help you remember the two sorts of things. A lens, aka an ordinary polymap, goes forward on positions and backwards on directions. So I write it with a forwards and backwards arrow. That's just one arrow, but it's forwards, backwards. And the chart goes forwards on directions and forwards on positions. And that's written with two forwards arrows. So then there's a crucial way that these things relate, and that's in a commutative square. So let's see if I can fit this in here without getting too small. Is this visible? See if the. Thank you. So suppose I have something that's like a square here, and it would be a commutative square normally if these were all the same kind of map, but they're actually two different kinds of maps involved in this commutative square. So here we have a chart, here we have a chart, and I'm going to give them names. This I'm going to call F. This one I'm going to call G. And then this lens I'm going to call W. And this lens I'm going to call V. And so what it means for something like this to commute is going to be that there are two equations satisfied, and we can think of it as both of the constituent squares commute. So on the bottom, there is a square, and that needs to commute. So what does that mean? It says for all I in P1, we have that V of f of I, so that's that top thing, equals the bottom thing. So equals G of W of I. And then we need the going up directions to commute as well. But to do that's a little trickier, because to go up, we need extra information around the base. So the other direction says that for any I in P1, and for any, as I'll call it, x, sitting in, I'm sorry, this should be P1 here, P11, in P3 sitting over Wi, then we'll have this equation here. So the equation is going to say I go up here, and then I go over. So I can go up here, W sharp, and I can take in I and x. And that brings me to something in here sitting over I. And then I have f flat, and f flat takes something sitting over I and gives me something sitting over f of I. So I can do f flat of this, and it's I, and I get something sitting over f of I. And that's going to equal going along the other way. So if I'm here, right, I can go down here because I have something, I have g flat. So I have something sitting over wi, and I can take g flat of it to get over here. So I would take g flat of wi of x. And now I'm in P4 sitting over g of wi. But g of wi is equal to v of f of I. So it's something sitting over v of f of I. And therefore, I can apply v sharp to bring myself back up here. And it goes in here is over f of I, here. And these two things sit in the same place in P2. They sit over f of I in P2. So that's what these two equalities, here's 1 and here's 2, are what it means for this square to commute. And I should say this, if you're looking to follow along in the book, this is, and you want to just have these equalities there the whole time, this is, appears in definition 4.3.3 of my book, which you can find at this GitHub. And it should compile this time, hopefully. All right. So I'm going to pause for questions for the chat, for anyone in the room. All right. OK, so last time what we saw is that a morphism of systems, so we saw that a system can be understood as a lens into a poly which represents its interface. So this is a system, and it reads out R. So it reads out R into P1, and P1 here is the outputs of this interface. And the update here takes in a direction out of the output and gives us a new state up here. So we saw that this is the same thing as a coalgebra. And a coalgebra, so this is the same thing as, let's say, S to PS. And we also saw that coalgebra morphisms, which look like this, are the same as squares in that commuting sense back there of this form. So what does that mean explicitly? Well, if we run through the equations again, where this one here is u prime, r prime, what this means, what both of these pictures mean, is that r prime of phi of s equals r of s, and u of phi of s at some input I is equal to phi of u of s at the input I. So that's just specializing the equations of a commuting square into this kind of particular square where the top is of this particular form. It's sy to the s, and this one's ty to the t. And this morphism here sort of does phi in both places, right? And that's part of the reason we really wanted these to both be covariant, so we could apply phi in both places in the same direction. And it means these equations. So that's where we left off last time. And so this time, I want to talk about what a morphism like this could be if we're allowed to also change the interface. So this thing is a morphism of coalgebras. So a map of coalgebras of P, K systems, Ka systems with interface P. So what if we were going to map from things that are in fact not from P to P, but what if we went from P to Q? So what if we did this? We allowed something a little more general here. So what would that be? So this is what we're going to talk about today. So before I do that, I want to, yes?
Quick question. One of those in that equation there should be a mean time, I think.
Yes, thank you. There it is. Thank you.
I think there's another question. We're talking about endo-functor co-operators. Does this story generalize to co-monad co-operators?
So every co-algebra in this sense is the comonad co-algebra of the free comonad generated by this polynomial. But no, this story, as I'm telling it right now, doesn't particularly generalize to arbitrary coalgebra morphisms in precisely this way. Although you can tell it very similarly, but you need a different double category. The double category would be the double category of functors in this way and co-functors in this way. And if you do that, then you would get that story. But I'm not going to talk about that. I'm just going to be using these bare interfaces that don't have extra goings on. OK, so cool. So that was 0. I'm going to leave that up for a little bit. Now we're going to switch to 1. We're going to see how behaviors can be squares in the double category of arenas. So let me give you a certain, so what do I mean by a behavior? By a behavior, I mean that a system can do something as it evolves, and a behavior will be a particular kind of thing it can do. So there's going to be a lot of different kinds of things that systems can do. I'm going to tell you about one now. We can have steady states. So my definition, so for a system, you are, it goes sy to the s to p. So this is a system with interface P. So, and a given output, O, in P1, and a given input, which is valid for O, so that sits over O in P, right? A IO steady state, this is the thing I'm defining, is an S in S satisfying this. R of S is O, so S is a state. A steady state is a state. And it outputs the chosen output O, and it inputs, and when you input I into it, it's steady. It stays the same. So one thing I want you to note is that we do need to say ahead of time what we want the output to be. Because remember, what we're allowed to input into our systems in the poly framework depends on their orientation in the environment, their position they have in their environment, or what they are already outputting. And so for that reason, we start with an O. And then we ask that the state here is reading out that O. And when you update it on the input, you get itself. So if I can turn your attention to this example system, these are my two examples. They're going to be kind of running examples. But let's just look at this one. which I call S1. And in S1, it has quite a few steady states. So a steady state in a diagram like this is a transition diagram. A steady state is a loop that just starts and ends at the same node. Now, what is the I.O. here? If we look at this state up here, state 1, 1, you can see that if I input false, it goes to itself, and it outputs blue. So this S11 is a blue false steady state, right? Now, note that S11 is not a true blue true steady state, because if I input true, it goes over there. So being a steady state really depends on what you're inputting at the time. Yeah, sure. Boop. Is that better? Whoa. Should have done that the whole time. All right. Okay. So yeah. So this has a lot of them. You know, in preparation for what I'll do later, how about we go ahead and actually write up what all the steady states are. So we can make it a little like matrix over here. So here is going to be P of 1. And so the possible outputs are true and false. Whereas the possible inputs, if I can get really colorful over here, are red, blue, and brown. It was originally green, but we don't have green markers. And so what you can see here is that, okay, let's do a little calculating here. How many true blue or true red steady states are there? Well, there's this one. If you do true, you're steady, and it outputs red. So this one here is the true red steady state. And how many blue true steady states are there? Well, there are none. If you ever are in a state that outputs blue and you hit true, you go somewhere else. So this is empty. And how many brown true steady states are there? Well, brown, there's only one brown state, and it always moves. So there's none here, and there's none here. OK, so what about a red false one? Well, if I'm in red, I must be up here, and if I do false, I get somewhere else. So this is not, this is empty. But what about blue false? Well, for blue, it's either this state or this state, and both of them, when you hit false, you go there. So in this one, we could either be in S13 or S11. So we could write this up a little shorter as 1, 0, 0, 0, 2, 0. OK, so that's just showing you how we can compress the information of where the steady states are into this matrix. And we'll come back to that later. OK. So there is a special system. So there's a special system which just is a steady state. And what that is this system. So effectively, it's going to output sort of whatever, just something, a single thing. And it takes in a single input, and by convention, our single input is always next, exclamation point, just next state, next. And it just stays at the same state. So what we could write here, right, the states here is 1. So it's 1 watt of the 1. And it has one output, 1. And it has one input, which is next. So this is here. And what does it output? Well, we'll say it just outputs whatever its state is, which is just anything. And then what does it update? Well, it just does the same thing. It stays fixed. So we could write this as also, it's not quite identity because it could take two things, but it's roughly the identity. It just does the same thing on its single input, which is next. OK. It is the identity map on the poly Y, in other words. So the really cool thing about this is that this will turn out, this is a special system. It is itself just the steady state, this kind of behavior. And it will turn out to represent the notion of steady state. So first, let's note this. Note, so a pair, the pair I in P over O, and O in P of 1, is a chart. And the chart goes from Y over to P. So why is that? Well, remember that a chart, so Y is 1y to the 1, just to remember. And a chart is a map on, well, I don't have to put that there, but a chart is a map on Y of 1 to P of 1, and for any I, or I'll use a different letter here, J in Y of 1, and for any thing sitting over J, we get something sitting over that here. So I'll call this O. So that's just what it means to be a chart. But in here we have a very simple poly on the left. So we can calculate this quite explicitly. Y of 1 is just 1. And a function out of a one-element set is just an element. So this thing is just the data of that element in P1. And similarly over here, well, we take something in Y of 1, but there's just one element, so we have no choice. And then we take something sitting over it. But sitting over, the only direction in Y is one thing. So we again have no choice. So this is, again, just the information of an element sitting over O. So that's why a chart over here from Y to P is the same thing as the pair of outputs which we needed to specify a steady state. And in general, this is why I ended up calling this thing a chart, because it's going to chart out our behavior beforehand. Okay, so then we can notice this. So given one of these things here, IO into P, and then we have this system, SY to the S, like this, UR over here, we can take a map out of this fixed point system, the steady state on its own. So what is that? Well, it's a chart like this, and this chart here, right, it's of the form SS. I'm always going to take my top charts between SY to the S and TY to the T. I'm going to take them to be the same map on both. And so here, this is 1 to S. So that's just a state. So what would it mean for this to commute? Well, what it means is that both squares commute. So in here, if I go RS, so R of S equals O. And then here I go I at S, right? Or I equals, and then I could go here and that, sorry, update after I at S equals S. Update of S, I equals S. And so I don't know if we could, if you get a good shot of that, and then we can maybe look back at these equations over here. We can kind of see why these equations over here are specializing to those over there. So in this case here, V sharp is U. F here was S. G flat over here was I, just the data I. And F flat here was S again. No other information. All the other information is just shuffling ones around. And so this equation here is the one that's telling us that it's actually a steady. Okay. So now that we know that, let me do another example. So these are steady states. Yeah, let's see if I can do another example up here. Blocking's not so good. Okay. So here's another example of, so I will say this, is that we say that this is, so the fixed point thing, this is called the fixed system. Fix represents steady states. So maps of systems out this way correspond to steady states. And note that the map of system here changed the interface, and that was important. That was part of the data we needed to define a steady state. Okay. So every sort of behavior that a system can do is going to be represented by a system which just does it. So here's another example. So, given a sequence OT in P1 and a sequence IT in P sitting over OT, then a IO trajectory is a sequence of states, ST, satisfying two laws. The readout of the state ST is OT, and the update of the state of ST at IT is ST plus 1. So what is one of these? Well, if we look at this picture here, a trajectory here would, well, first we need to have a sequence of inputs, right? But remember that in the Poly formalism, to give it input, we need to know what output it's valid for. So that's why we also need that sequence of outputs. So if we start here, say here, and then we do true, let's say our sequence is true, true, false, true, true, false, something like that. And we started here, then we would output blue, and hit true, we'd go here, output red, hit true, stay here, output red, hit false, go here, output brown, and then hit true, output blue, hit true, output blue, and then hit false, output blue, and so on. And that would be a trajectory, and that sequence of outputs would be part of its chart. So I say that this is here is this thing here is the chart of the trajectory. Since it charts out the path it will take, at least with regards to the outputs we see. And I just want to remind you that that's something that we need to have both the outputs in order to make the inputs well defined. And that's why I call maps charts, because surprise, surprise. So note, again, that the sequences, so OT in P1 and IT in P sitting over OT is a chart IO, this time from NY over to P. So why is this? Well, again, a chart is forward on both directions. So on positions, we have O going from N to P1. So that's our sequence of outputs, O. And then on directions, we have I, and I takes in something in here, in N, a position here, and a position sitting over it, but there's just one, so it's just, one. And then it gives you something sitting over the output here. So this is OT. So you can see that in total, I is just a sequence of outputs valid for, of inputs valid for the given sequence of outputs. So now, just like we had a special system, which is a steady state, there is a special system which is a trajectory. And this one is, it looks like this. So its states are the natural numbers. It has one input, which we always call next. And on every next, it just counts up by 1. So we could think of this as a form of timeline. So I call this one time. And so what is it explicitly? Well, its states are the natural numbers, so it's ny to the n. And then it's a system, so it goes from ny to the n to ny. And it's going to just output its own thing. So its output is identity. And its update is going to be +1. So what does that mean? Well, here I have an input which is 1, so it's next. And when I hit next, what do? I take n, my state, and I go to n and by adding 1. So now we can start to look at what it would be to map out of such a system. So I'm going to erase a little bit here. So over here in this position, where before I had the fixed point 1, I'm going to put time. And this is going to be +1. And then so what is a chart up here of the form SS? Well, S is a function from n to s. So it's a sequence of states. And what does it mean for this to commute? Well, first of all, if we do the top here, it's the same as this. So that means R of ST is equal to OT. And if we go this way, it's the same as going this way. So this way says U at ST of IT equals, and then we go this way. So this way says add 1 to t, and then do s. So you can see that the equations that make something a trajectory are precisely encoded by this commuting square in the double category of arenas. Okay. So there are many other things like that. So maybe I have we saw like the fixed point. We saw time. But there are also maybe clocks of various lengths. So however many hours this is, we can imagine here. Oh, I need to say, this means time, that system on the left, represents trajectories. So represents means that maps out of this system are those things. So this kind of system here is going to represent cycles of length, well, 1, 2, 3, 4, 5, 6, 7. 7. And we can also have other things, like maybe, you know, you do two things for a little bit, and then you go into a cycle of length 3. Or maybe you want to express how you do things with multiple different inputs, and you can totally do that as well. Any one of these systems is a pure shape of system, and the map out of it represents that sort of behavior. So you can see each one of these systems is a way that a state can behave, a system can behave, purely distilled to a certain kind. And a map out of that, in the sense of one of these squares, where the bottom is allowed to be any chart, is a behavior of that shape. So that's the end of part 1. I'm going to take a moment for questions while I prepare for part 2.
Quick question. This time thing, so is that the ny or is that the ny?
Thank you. That's a great question. remember that the systems themselves are lens maps. So what time is this entire thing. This is time. And this is some other entire thing, which we call S. And this is a map. We can see this as a map, like here, over. But really, we don't want to see it as a single map. We want to see S as the single map. And we want to say, fix this. And then if you can fill in an S there such that this commutes, that's a morphism relative to this thing. And so there's a formalism for doing that, which I'm not going to get in. But there's another way to think about it, which cleanly separates the idea of the chart of your trajectory from the actual trajectory itself. But right now, we can think of it as, we can think of these squares as morphisms between polymaps. And in that sense, they give us morphisms between systems like this. Okay. Okay, I'm going to go on. So part 2, we're going to see, so in part 1, we saw how behaviors were squares in the double category of arenas. I hope that's clear from those 2 examples. It's worth seeing a lot more examples for it to gel. But now I'm going to show you how composing in the double category of arenas, so allows you to compose these behaviors. So first of all, I want to remind you about the double category of arenas. What does it mean? Well, you see, we have arenas, or polys, and whenever I'm talking about them in this way, I'm going to call them arenas. So when we have these arenas over here, they can be the interfaces for systems. And the double cat, we have 2 different kinds of morphisms between them. Excuse me. We have 2 different kinds of morphisms between them. We have the charts and the lenses. And that's sort of and then we have this notion of commutative square between them. And that's sort of the idea behind a double category. You have 2 different kinds of morphisms in your category, but you have a notion of commuting square between them. And so what it means to be a double category in particular is that if we lie these squares end by end, either next to each other horizontally or next to each other vertically, then we get squares again when we compose in the respective categories, the chart one or the lens one. And so I'm going to show how those 2 sorts of composition can help us understand what we're doing here. So one thing I can say, first of all, I can just modify this diagram here. So we just saw how maps from time to S of this form, the squares of this form, are trajectories. Well, so what if I have any other system over here with any other interface, and we have any other charts over here, like this, and we have any other map over here of systems. This could even be the identity, like a map of coalgebras. So if you remember last time, we saw how maps of coalgebras are sort of like simulations. And for that reason, they should induce behaviors. If your thing behaves some way and it's simulating something else, then that other thing should behave that way. And what you can see here is that we can compose these squares horizontally, like this. And in the end, we get a map here from time to t, which corresponds to a trajectory. And for that reason, these maps of systems preserve any kind of behavior we want. So that's the easy way, is seeing this horizontal thing. But that's not that interesting, after all, because these sort of maps of systems are defined in such a way that they sort of have to preserve all observable behavior. So it's kind of something you would expect. What's more interesting is composing in poly, right? So this is composing with charts, which is something I told you about last week, and it's kind of a new notion that's just to make this story work. But you've seen in the rest of the course polymorphisms. And so now, which I'm calling lenses, they're the vertical ones. So composing vertically is going to be a little more interesting. So let's see that here. Okay, so remember that a wiring diagram can be understood as a polymap or a lens. So here's my wiring diagram. And then I'm going to label these with sets. So this wiring diagram in here corresponds to the following lens. So what do? We're going to tensor each of these boxes. And each of these boxes, we're going to take the outputs and the inputs and turn it into a monomial. So this one outputs D and C, and it inputs B. So it's going to be like that. And then we're going to tensor it with something which outputs B and inputs C and A, or A and C. Okay? And the whole outer box goes below, and that's outputting D and inputting A. And so the wiring diagram itself is a lens of this form. And so explicitly, what is it? Well, W takes in three things, right? It takes in B, D, and C. Sorry about the ordering, but it's clear that the data is still there. It takes in B, D, and C. And W sharp here, well, it takes in B, D, and C as well. And it also takes in an A from down here, and we have to go back up. And we have to give something in B, A, and C. So it appears that, I should have written this tensor the other way, because that's how my notes are. So this is explicitly, these two functions represent this wiring diagram. And what you can see is that they tell you how to get the information from the inside out. So W tells you how to take any output here. So B is sitting on the output here, D is sitting on the output here, and C is sitting on the output here. And how do you get the output out here? Well, it's connected to D, so you pass D forward. And W sharp tells you how to input into a system. So W sharp says that, okay, if the system's waiting at these certain outputs here, right, and it gets from all the way outside an A, then what do? Well, you feed that A and the C, which was sitting out here, into this one. And then you feed the B, which was sitting out here, into that one. So that's this. Simple. Excuse me. Great time to be coughing. All right. So let's see what a square of this form is for this diagram here. I'll take this opportunity to write it in the right way. Excuse me. I actually want to write it below. Y plus y. Then I'm going to do B, Y, A, C, tensor, D, C, Y, B, then D, Y, A. Okay. So I want to see what a square of this form is. Okay. So remember that charts out of Y just pick out elements. They just pick out positions and then directions sitting at that position. So over here, what this is going to be is it's a position, we'll call it B1, and then it's also a direction, positions D1 and C1, and then directions A1, C2, and B2. And down here, we have D2 and A2. And so what this square commuting means is these two equations, which I'll write over here. It means that W of B1, D1, C1 is equal to D2. So that's this way equals that way. And the other one is W sharp of B1, D1, C1, and then A2 is going to equal A1, C2, and B2. Is this visible? Okay. And so, cool. So that's just reading off what the formula for this square means. But now we already know what W is, right? W by definition is actually D1. And W sharp by definition is actually A2, C1, B1. So what you see is that this square here tells us that, in fact, D1 equals D2, A1 equals A2, C1 equals C2, and B1 equals B2. All of them are equal. And what does that mean intuitively? Well, this thing here, in other words, such a square like this, is a pair of outputs over each of these things and inputs that are valid for them, and outputs at the outer ones and outputs and inputs at the outer ones that actually get passed to each other. They actually are compatible according to the wiring diagram. So a square like this is a bunch of data sitting on that wiring diagram. Now, in addition to being able to compose horizontally, we can also compose vertically. So if I put here my system here, which is fix, and I'll mark out where it is, this is going to be the system fix. And I put some, say I have two systems like S in here and T in here. So it's SY to the S, and so TY to the T. And this is U R tensor U prime R prime. And let's say I have something here, which I call S comma T, S comma T. What does it mean? So I'll just, right here, this thing here. So this thing here is S tensor T, right? So the fact that I have, so this, what is this upper square? This upper square is a steady state in this combined system. In other words, it's a pair of steady states, one in S and one in T. But then we can compose on the bottom with this square. So on this side, what does that do? Composing on the bottom gives us the composite system. Composite, I don't know how to say it. Compose under W sharp and W. In other words, it's the outer box here. It's what fills the outer box after we're done filling in the inner boxes. And over here, well, it's just the identity. So in other words, this thing here is also fixed. So a map out of it is a steady state. Now, it's no longer an A, C, B, B, D, C steady state. It's an A, D steady state, right? But it's still a steady state of the combined system. So what the composing vertically in the double category shows is that behaviors wire together. And so if you have a behavior of the parts, you get a behavior of the whole. And it's in fact a theorem, which is not too hard to show, that if you, as long as the representative of your behavior exposes its entire state, in other words, this readout function is an identity, then you can go the other way. Every behavior of the whole induces behaviors of the parts. Okay, so let's see that in an example. So if we come back over here, we have all our steady states here. Let's do this one. So this one instead, well, it's a little longer. Just a little bit. This one, it outputs true and false, and it inputs red, blue, and green. Red. Oh, sorry. Blue and brown. Okay, so red and true, well, here's one doing true, and here's red fixed. So this one is just S21. Red and false, well, no. The false is red moves around. Oh, and the true here, red moved. Okay, so let's look at blue loops. This one and this one, both in true. So this is S12, S23. And on the other hand, are there any false blue loops? No. And here we can see that there's a false brown loop, but no other brown loops. 2. Okay? So if we just count them up, we'll get this thing, this matrix, which is a little smaller. I'll write it down below, which is 1, 2, 1, 0, 0. Okay. So now we know all the steady states for these two systems. What is a steady state for the wired together system? Well, a steady state for the wired together system, by this kind of calculation over here, is just going to be a steady state for each of them. So in other words, a steady state for the wired together system here, which wired together system I should say, let me wire these together. I didn't leave enough room for the wiring diagram here. I'm going to cannibalize my introduction right there. Oh yeah. I'm going to wire these together like this. Here's S1. Here's S2. I'm going to just wire the input of S1 into S2. Like that. Wire them directly in. So you can see S1, it takes in true and false and outputs red, blue, and brown. And S2 takes in red, blue, and brown and then outputs true and false. Okay, so if we have so what are the steady states of the combined system? The combined system is something which, well, we can see it as having a state both in here and in here. And then when you input something in true false, it updates S1, then spits out that, then uses that result to update S2 and spits out the result. So in other words, let's suppose we were here and here, and we took in true. So here we took in true, we go over to here and we spit out red. And here we're down here and we take in a red, we go over here and we spit out false. Okay. So what would a steady state of the combined system be? Well, it's got to be a steady state in each. But it's got to be a steady state in each that actually like the output of the one has to be the thing that makes the other one steady. So for example, if I'm in here and I see true, then I go on a loop and then I output red. Now let's suppose I was up here. So I saw red and I go out here and I output true. So the pair this and this is a red true is a true true steady state. Right? So the true up here and the true down here, together it's a steady state. And that's what all of those steady states are. So what we could do is figure out how many true steady states there are. So I'm going to write it out here. You have true, false, here. Okay, so we saw that there's a true steady state. Right? Are there any others? Well, there's no other true loops over there, so no. There's one true steady state. Now let's look at a true, false steady state. Okay? So a true, false steady state means that we input true to the first one, so it has to be a true steady state here. And then it has to output false over there. So what is it? So let's see. True is red. So red has to be a loop, but there's only one red loop here. It's already true, so there is none of these. Now what if we look at about a false true? That's if we input false to the first system, it does its thing, outputs something that makes the other thing be steady and output false. So false steady states in the first one here, there are two of them, and they both output blue. So that's pretty good. Now over here, let's look at where blue steady states. Well, you can see that there's two of them, and they both output true. So there's in fact a lot of false true steady states. You can take any pair of these with any of these, and it will be a steady state. So there are in total 4. Now for false, if we take in false, right, the only steady states are the blue ones. But the blue ones here are all true. This one, taking blue, it yields false, but it goes somewhere else. So there's 0. And there's one really magical thing you might notice about this matrix. which is, if you're quick on your feet with matrix arithmetic, is that this matrix is the product of those two matrices. And that's pretty wild. Because it's especially wild if you happen to know string diagrams for doing matrix arithmetic. So if you happen to know the string diagrams for doing matrix arithmetic, this is going to blow your mind. Because if you look at this diagram, this string diagram, this is the string diagram for multiplying matrices. So this was what David noticed, the other David, is that if you take your string diagram that describes how you compose your systems, and then you take the matrices of steady states, and then you read this string diagram, something like this, not as a wiring diagram for how to compose your systems, but instead as a string diagram for how to multiply your matrices, and the loop here is something like a trace, a partial trace, then what you get is the matrix of steady states for the output. And so this is a really remarkable theorem. It's really quite beautiful. And I don't think I'm going to have time today to tell you how it follows from the full story of how it follows from the double category, but I'll give you a taste. So this is remarkable. It's a beautiful kind of thing where you just get, you look at the same diagrams and you're like, hey, I've seen those before. So it's not just true for steady states. It's in fact true for any kind of behavior whatsoever. As long as you output the behavior, the system that represents your behavior that just is doing that thing, as long as it outputs its entire state, then this theorem will hold. And the way it works is this. We note that every linear operation is represented by a matrix. That includes matrix multiplication, because matrix multiplication is linear in each matrix. So in fact, this string diagram, this wiring diagram here, considered as an operation on matrices, can be associated to a big matrix. So how big is that matrix? If this is O1, and this is I1, and this is O2, and this is I2, well, first of all, we need that O1 equals I2, so this is, let's say, X, right? So how big is one of these, the matrix that tells us the linear operation of multiplying two matrices? One which is O1 by I1 O1, and one which is I2 O2? Well, it's I2 by O2 by I1 by O1. And here let's do a little rewriting here. This is our middle X. This is our middle X. So it's a this many matrix. Oh, sorry, it's even more, because I have to end up with something. So it's this by what do I end up with? I2 by O1. So it's a this many matrix. You see, it's a matrix represents a linear map, and sorry, I always write my matrices backwards. It's this by this many matrix, and because it outputs an I2 by O1 matrix, and it takes as its input an I2 by X by O1 matrix, which is to say both of the matrices put tensored together into blocks of a big matrix. So that's a really big matrix, and you might wonder, why would I make every life so much more complicated after I made it so beautiful by telling you this is the string diagram for composition? Well, the reason is that this matrix is extremely easy to describe from the double category of Arena's point of view. This is the matrix here. If we go to this wiring diagram over here, so this wiring diagram corresponds to an even bigger matrix. But the matrix it corresponds to is the matrix that takes, it's a how many charts do you have this way by how many charts do you have this way matrix. And the matrix has either entries 0 or 1, and it has an entry 0 if there isn't a square here, and it has 1 if there is. So in fact, this follows from the representability theory of double categories, which is sort of an established theory by Bob Perret. And so when the dust all settles, you find that not only do steady states compose according to matrix arithmetic, but all behaviors do. Thank you. Are there any questions? I'll, blew through that last part.
I have a question.
Yeah.
So, how much does this generalize to behaviors other than fixed points?
It generalizes exactly, except your matrices become really, really big. Because it's a how many, like for example for trajectories, it would be a all trajectories by all trajectories matrix. So a sequence of a matrix which is all sequences of outputs by all sequences of inputs by all sequences of outputs. And yeah, so that they get highly infinite. But if you're wondering what is an infinite matrix, the real way you think about this is a matrix of sets. In other words, a span. And so if you're allowed to take these matrices of sets, then it doesn't matter how infinite they are. You can still do matrix arithmetic with them. You can still interpret the string diagrams there. And that's where the result really lies. When you have finite things, like for example, I erased them, but for example, periodic orbits of any fixed period, they remain finite when your system is finite, right? Just like steady states. And so in that case, you really will get these integer matrices that you can multiply. Neat. Thanks.